welcome to Module 4 of 1109 on control flow and functions and problem decomposition. So the assumptions for this module are that we have a basic Python setup, which we established in Module 2, and we can run a Jupyter Notebook. I assume you're comfortable with variables, that you understand basic types like integers, floating points, strings, and Boolean, and you can understand simple expressions, which we covered in M03. I expect that you've already seen a Python list and basic for loop syntax, but you might not be entirely fluent yet. And I also wanted to establish that all the data sets in this deck are still going to be tiny and created inside this notebook when you run the code. So far we have completed modules 1 to 3, and now we're going to be focusing on control flow and functions. Later on, a lot of what we're establishing now will be used in debugging and doc tests. Later on, we'll get deeper into pandas and then real tabular data, although toy data sets will still come up from time to time. We're going to talk about control flow and functions. This is the kind of fundamental grammar that you will use in every data science module, both in this class and in the real world. And we want to establish some good habits early, so we're going to focus on reproducibility and testability to make sure that analyses later on are robust and realistic. So today, by the end of this module, you should be able to trace and predict the behavior of simple if, else blocks and for loops. You'll be able to write small single responsibility Python functions with clear names and doc strings, although we won't talk too much about doc strings. You'll be able to use control flow and functions to answer some basic questions about tiny data sets. When I say answer questions, I mean provide code that can answer the questions for you. You'll be able to explain in plain language what it means to treat a function as a black box, basically mapping inputs to outputs. You'll be able to decide whether a refactored solution is good enough using simple data science quality metrics like readability, reuse, and tests, although this in particular, and indeed everything else I just mentioned, are skills that we won't establish once and for all today, but it's just one step on a long journey of continued improvement. Let's start with the conceptual scaffold. Just some key definitions. So a control flow basically describes how a program chooses which instructions to run and how many times to run them if there are multiple available to them. You must have seen this already in some of your programming classes. So branching is a situation where the code gets to a certain point. There's various paths it might take, only one of which might actually be taken at a time. And in Python, we choose which paths to go down using the if statement, the elif statement. Elif is kind of abbreviated version of else if, and finally else. We'll show you an example of this in a moment. Repetition is where you have a block of code and you repeat that code over and over again for as long as some condition exists. And there's two primary versions of this in Python, the for loop and the while loop, and we'll see these soon enough. Beyond this control flow, telling the computer which path to go down, how many times to run certain code, a function is sort of a reusable block of code that can be used over and over again in multiple different contexts. As the name suggests, it performs a particular function, ideally a very limited function in most situations. Functions take inputs. Sometimes these inputs are called parameters. Inside the function, it does some specialized work on those inputs, and then often it will return an output. This is a bit of a side note. Sometimes old school computer scientists like myself might refer to a function that provides no output as a procedure. So a procedure still might take in inputs, but then produce no output. Functions generally produce outputs, and in common parlance, functions that don't produce outputs are still functions. And returning back to the control flow of this slide, the problem decomposition is the task we've been performing already in this class that we'll be continuing to perform in other modules. This is basically the abstract task of breaking down a messy problem into smaller testable pieces that we can evaluate and ideally implement as small functions. So the function we can be very confident does the right thing, and then we can reuse it over and over again. So this is good data science hygiene as well. The idea is to break large problems down into small tractable problems. It's sort of like building a watch. You don't build a old-fashioned watch or indeed a new smartwatch all in one go. You build them module by module. You make sure every module is functional, and then you kind of piece it together afterwards in a sort of hierarchy of modules. So the general idea of starting with data and using the data to produce code and using that code to come to a decision about something is a pipeline that we're going to see over and over in this class. Today we're going to focus mostly on just this one box over here in which we apply control flow functions along this overall pipeline. So we'll start with data in this marked box for now. How good control flow and functions help us go from data to evidence is the topic of today's module. And later modules will deepen this data generating process, describe more decisions, costs, ethics, although we'll talk about those briefly at the end of today. Here's a quick example of what not to write. So since you're perhaps early on your coding journey, your data science journey, you might not have already developed the strong programming habits. So you might not recognize that this block of code over here is not necessarily ideal. It might run, it might provide correct output, but there are various problems with it. In this example, the idea is that we are storing the minutes spent studying classes on a day-by-day basis, and then we're using some control logic to decide whether or not we've had a long study session on each of these days. As you can see at the very beginning here, we have Monday minutes studied as 25, Tuesday minutes studied as 40. Each of those is stored in their own variable, which also might not be the best idea. And then down here at the bottom, we have a series of decisions that we make based on the values of those variables. So if the value stored in the variable called Monday minutes is greater than or equal to 40, then we'll print out this long session on Monday. I don't think it's necessary to mention this now, but just because this is a first-year class in Python, I'm going to go step by step a little bit. One thing you might notice here is that there's no parentheses around this decision here of whether Monday minutes is greater than or equal to 40. Other programming language might put parentheses to the left of the variable and to the right of the value. In Python, that's obviously not necessary. What is necessary to mark the end of the conditional, the Boolean decision in this case, that's deciding whether or not to go into this appropriate step. We have this colon. So if the condition here is true, this colon basically means then, we're going to run this next line, line 7. Now, Python has this issue of indentation. In other programming languages, we might have brackets that demarcate this block that we'd either run or not run, depending on whether this condition is true or false. In Python, this is all determined by indentation. We're not going to spend too much time on this now because this is not a programming class, but everything that's indented below line 6 at a deeper level will be run until we keep on reading and then pop back out into an indentation level that is fewer indents, i.e. Line 9 in this case. And here there's only one line that's indented, line 7, so if the condition on line 6 is true, we will run the code on line 7, and if it's false, we'll skip it and move on to line 8. One more last note, this indentation can take various forms. This is almost a cultural battle between those who prefer tabs here. So this might equal 1 tab that I've highlighted over here. This might also equal 1, 2, 3, 4 individual spaces. Python doesn't really care whether you use tabs or spaces or whether you use 3 spaces or 4 spaces, as long as it's consistent in these blocks. So the best way to determine which side of the fence you fall on is just to start coding and determine what works best for you. Regardless, as you can see, when we've got to this point, line 6, we test the condition of whether Monday minutes is greater than or equal to 40. We remember that the value stored in the variable Monday minutes is 25, so therefore this is not true, so we're going to skip over line 7, move on to line 8. Nothing's on line 8, we move on to line 9, and so on. In this case, by the way, Tuesday minutes is greater than or equal to 40. In fact, it's exactly equal to 40, so this condition is true, and therefore we we'll go on to line 10 and print out long session on Tuesday. So here's the reason why this code isn't the greatest code in the world. This is a warning. There's repeated logic. So we're testing the same logic, essentially, for every single day for which we have minutes stored. We test whether Monday is greater than or equal to 40. We test whether Tuesday is greater than or equal to 40, and so on. Wouldn't it be better to have all of this logic in one single conditional somehow, where we didn't have to have the risk of extra code? The more code we write, the more likely we are to produce bugs. Similarly, if we wanted to change this threshold of 40 minutes to something else, maybe we're more ambitious and we want to aim for 60 minutes, we'll have to go through all of our code, find all of the 40s, replace them with 60s. What happens if we miss one by accident, which is another possible problem? If we only have one condition with one threshold marked 40 once, then it'll be a lot easier to change, which is the second indication here. So in this case, the person is becoming less ambitious. A long study session goes from 40 minutes to 30 minutes, but you get the idea. Similarly, it's harder to evaluate this. At some point, we're going to want to add code that tests whether or not the overall logic is correct. And there's no single place where we can really test things. We'd have to test the first block with regards to Monday, the second with regards to Tuesday, and so on, and add a lot of extra code for all this debugging. So there's at least 3 problems here. The first one I mentioned has to do with the fact that the more code we write, the more likely we are to introduce some bugs, which is a problem. The second problem is that if we wanted to make some changes to the code subsequently, we wanted to change our logic in some way, we're going to have to do extra work and be extra diligent to make sure that the new logic is implemented entirely throughout the file. And then the third problem is that debugging is going to also have to introduce a lot of extra code because there's no single place to do the debugging. A fourth possible issue here is that it's just a bit more ugly. So like, as a human reader of this code, you prefer code that is as simple as possible, but not simpler. So we can do better than this, as you might have expected, using control flow and functions. So this is a bit of a different challenge. Now we're not measuring minutes of studying, we're measuring another step counter. But we're going to use the if statement, the else if statement, which is written ELIF, and the else statement. So now we only have one variable, the number of steps we have. And we still have 3 possibilities. Either we've exceeded some stretch goal, or we've just exceeded some baseline target, or we've not exceeded either. So we've embedded that within this code block over here. The first thing is our stretch goal. So here we have a stretch goal of 10,000 steps per day. We just evaluate whether or not the steps is greater than or equal to that, and it isn't. So we jump ahead. We skip this block over here. That's part of the first conditional. We get down to line 5. And then again, we have another evaluation. So it's not true that steps are greater than or equal to 10,000. Else, if the steps are greater than or equal to 8,000, I want to print out, the label is going to be on target in line 6. Again, perform the evaluation. Is my steps greater than or equal to 8,000? Well, it's not. It's close, but it's not really that. It's not over the target. So therefore, this condition is also false. Therefore, the else if statement is false. I skip over line 6 and move on to line 7. Line 7 here is else. So this is sort of a catch-all. So if all of the conditions above were not met, I'll end up here at the else, and then I'll just perform whatever code exists in its respective little block. You can have as many else ifs as you want. So you can have an if statement initially, which checks some initial statement. Then you can, if that's not true, you can go to the first else if, and the second else if, and third and fourth and fifth, and so on. And then you end up at the else at the bottom. Python doesn't require you to have this else statement. If you're merely, like, maybe you want not to do nothing at all, if you've met neither of your stretch goal or your basic target, you don't want to set anything to the variable label. So you don't necessarily have to have code for 7 or 8 for this still to be a valid Python, but it's still a good practice to sort of, as a data scientist, account for all possibilities and write up all of these little blocks. So again, here we don't have to run a conditional, we don't have to run multiple conditionals. If it's the case that the steps is greater than or equal to 10,000, then we'll just run line 4, and then we'll bounce right out all this entire block of if, else, if, and else statements, and then get down here to line 9. So if the condition on line 3 is true, we do not have to run the condition on line 5, and we don't have to catch ourselves on line 7 either. So we're only going to run one branch, and moreover, we're only going to run the minimum number of conditional checks. We're going to run these from top to bottom, like I just showed you. So first I run step 3. If that's false, I'll jump to the next else if, or else, depending on what exists. If that's false, I'll jump to the next, conditional check, and so on. So this kind of branching will allow us to do all kinds of things. It'll help us in data cleaning later on in the course. This will help us flag outliers. This will help us bin values into sort of partitions of data. This will all make sense later, but this is a nice, clean way to do to account for all accountable possibilities of, say, a variable in this case, or some condition in the world. It's clean, concise, and elegant. We might want to do something on a variety of variables now. So now we're flipping from conditional checks to the repetition I mentioned earlier. So the first one we're going to look at is for loops. In this case, we have a number of minutes we're measuring. Again, this is back to the study session. So perhaps on Monday, we've studied 25 minutes, on Tuesday 40, Wednesday 35, Thursday 50. And we want to just account for the total number of minutes we've studied. There are many ways of doing this, and there are lots of built-in functions that can immediately give you the sum of a list of this type in Python. But just for the sake of this explanation, we're going to iterate through every element of this list and add up the total value as we go. So to do that, we can imagine that we haven't counted any minutes yet. So it's currently Sunday. We haven't started studying yet. So here we've sort of stored an initial value of 0 in the variable total. And then as we move on through the week, we're going to keep on adding to our overall total, our overall sum. Down here on line 4 is sort of the initial syntax for a for loop. It has, 4 main components. I'll just mention them now. For, m, in, minutes. The for and the in part are immutable. We're always going to need those. The m is a variable that we can call whatever we want, and minutes is a variable that we can call whatever we want. Minutes here has to pre-exist, so I already have the variable minutes. There it is. It's a list of 4 elements, and I'm using it here. M I can name for the first time in this function, or in this for loop. As you noticed, I don't make reference to m, the variable m, anywhere previously. I sort of create it right now in my for loop. And the syntax is very close to the English language. In English, I might say something like, for every value in this list, do something with that value. And that's very close to what I have here. For some variable m in the list minutes, do, indicated by this colon, whatever is in this indented block below it. Here there's only one line of indentation here, so I'm only going to run this one line. And this will iterate over and over again for every possible value of the list in minutes, and at every iteration, the value to which it points will be stored in this variable m. So I welcome you to run this yourself. Hopefully this is very self-explanatory, and I'm just iterating over something you already know. The only thing I'm going to do now is I'm going to take my total that I have previously, and I'm going to add the value that I store in m in one iteration of this for loop to the total. I'm going to store that sum back into my variable total. All right, so the total starts 0. On the first iteration, m equals 25. 0 plus 25 is 25. My total is 25. I finished line 5 now. I can iterate to the next value in the list minutes. So now m equals 40. So I'm in the next iteration of this loop. I haven't finished iterating over minutes yet. Go down to line 5. Total is equal to 25 at this point. M is equal to 40. 25 plus 40 is 65. I'll store 65 in total. I finish this iteration of the for loop, and then I'm going to go back to line 4 and basically check if I finished iterating through minutes yet. I haven't. M is now equal to 35, and so on. Once I've run through every possible value of the list minutes, so I've run through this for loop 4 times, then the for loop is finished. I'll end up on line 6. Nothing to do there. Go to line 7. That'll just print the total number of minutes. Right? So total minutes, comma total. We'll write out the string and then the number total. There really should be a little space here between the colon and the double quote. You can fix that yourself. So these loops are useful for, or loops in general can be useful for things like counting. So in this case, I'm aggregating. So like I'm doing an aggregation of the total minutes per topic. What I could have done instead is I could have included within this block, instead of this one line total 5, I could have had a conditional. I could have checked whether the value m is greater than or equal to 40. And if the value is greater than or equal to 40, I might have incremented or added 1 to a counter of the total number of long study sessions that I've had, if long is defined as 40 minutes. So I could have basically just counted the number of times that I've exceeded 40 in my study minutes. I could have also searched for particular values. I could have iterated over every possible length of minutes over the list in minutes. And if there was a missing value, like an odd number or a value of a particular quantity, I could have performed some certain tasks. So I could have had some other conditionals within this block in every iteration of the for loop. So these are kind of standard uses of for loops. I mentioned that I wanted to get to functions eventually. So functions are a really good way to do data science properly. We like functions. They're small, concise, ideally, and therefore they can be tested very rigorously, and we can be confident in their use in subsequent scenarios. So you might have seen this already before, but I want to establish this again regardless. The syntax for a Python function is initially we have this special keyword def. This stands for define. It just means that I'm going to define a function now. The next bit of text I have here is going to be the name of this function. So this particular function is called is_long_session. And then I have the parentheses, open and close parentheses. This is the list of arguments that this function can take. I don't specify here whether I'm taking integers or floating points, although that's something you can do in Python if you want to learn how to do that. Here I'm just saying I take 2 arguments, or 1 or 2 arguments. These are going to be minutes and a threshold, respectively. So the first argument is going to be minutes. The second one is going to be threshold, but if it's not included, the default value for threshold will be equal to 40. So this threshold equals 40 here just basically means if somebody calls isLong function with only 1 argument, minutes, then just set threshold equal to 40 and then do your logic. Then we have a colon. Just like conditionals, just like for loops, this colon indicates that I'm going to have an indented little block, and that indented little block is, in this case, how the function is defined. Lines 2 to 4 is a multi-line comment. So these three quotes basically opens this multi-line comment. These other 3 double quotes closes the multi-line comment. Here I have 1 line of multi-line comment, but this is something that Python doesn't evaluate, but is just for our benefit to understand, what the code is doing, or in other words, for the coder to communicate to the reader of the code. In this case, this is a very simple function. It's a bit of overkill in my opinion, but you're basically going to return a single value. That value is going to be a Boolean function, and that value of that, or it's going to be a Boolean value, and that value is going to be determined by this comparison. If minutes is greater than or equal to the threshold, this is going to return true, otherwise it's going to return false. Okay? So a few things I want to point out is that a good function will have a clear name. You're not normally going to call your functions like f1, f2, f3, unless they're very generic. You're going to name these functions according to their function or their purpose. Here we're using underscores. Another way that coders like to break themselves into little camps is naming conventions. This is beyond the scope of this class. I understand that people these days like using underscores. I like using a different method, but just for the sake of this course, we'll be following this convention as much as possible. Usually we're going to have parameters, so functions normally operate on some inputs, like I mentioned earlier. Minutes and threshold, I called parameters a moment ago, but these are essentially the inputs. As I mentioned earlier, functions usually have a single responsibility. If functions are doing too much different kinds of work, their work becomes diffuse, it's harder to understand what they're doing, harder to debug, harder to understand, and so on. And generally we're going to have a single return statement, and there's not going to be too many hidden side effects that we have to account for. So generally, we have an idea in our head in English or whatever language you think in that we want to make specific. We can make that specific in code like we just did, and then we can test it in various ways, and then once we've tested it, we can reuse it. I want to jump into the math a little bit. So you might have heard of functions in math. So in math, a function might be written like something like this. We have a function f, takes an input x, and then how is this function defined? Well, this function is just x squared plus 1. So you can think of this function, this mathematical function, as a kind of machine also. You put in a value for x, and then you get out x squared plus 1, written out here as if it's code. The function we just wrote in code, which is long session, the function is long session, would be written in mathematical forms, like you might see in a paper or a mathematical textbook, in this way, right? So you have the function f with an input m, can be, in this case, either of two possible values. The conditional in mathematics is normally written over here on the right. So if m is greater than or equal to 40, then the function f of m returns long. Otherwise, or else, it returns not long, or it takes that value. So hopefully you can see here how we have coding representations, which we saw a moment ago in Python, of the same kind of operation. And you have the mathematical form. And often there's like a one-to-one relationship between these things. Coding can usually do a little bit more than most mathematical functions can, because there's a temporal procedure that we iterate over, but you can see that there's a pretty strong correspondence. So here, a function is this rule that always tells you what the output goes with a given input without surprises. In other words, if you pass in a particular input value, you get a predictable output value and not multiple possible output values. There is some differences there also between mathematics and coding. In mathematical functions, we normally expect there to be one single value of output for a function. Coding can be a bit more flexible, and you can return multiple values, but whether those are multiple values or not, or just a vector representation of, like in a single variable output, is another issue which I'm getting distracted by. So you understand the main point. This rule view, the idea that a function is a kind of rule, will matter later, because we're going to be talking about reasoning. We're talking about models and fairness. So the idea of a rule as a immutable fact of the world, in this case, what a long session is or isn't, is something we'll be returning to periodically. So just still focusing on the math a little bit, we have the idea of preconditions and postconditions. So what must be true, or what must be extant or existing before we call a function? So one thing that must be true is that minutes must be a non-negative number. When I ran the code earlier in Python, where I'm just adding minutes to a running total, I'm just adding those minutes together. But what happens if for some reason the minutes I have stored in my list, if one of them happens to be negative? That doesn't really make sense. You can't wake up one Tuesday morning and perform a task that actively removes minutes of study. And as I'm saying that, I imagine there might be certain ways that you might find a solution to that kind of problem. But in normal situations, you study for a particular number of minutes, and that number of minutes is accumulated positively. So you might have to do some kind of check to just check that the minutes m in minutes is non-negative, 0 or above. What are the post conditions? So what should the function guarantee after it returns? So here it's guaranteed essentially that the return value of is_long session minutes will be either true or false, just because of how we've structured things. But if we had written the function in a way that we weren't returning that actual conditional, but we computed the conditional before and maybe did some extra work and then we returned a value, what if we accidentally overwrote that Boolean value with something else? And suddenly the output conditions could sometimes be a Boolean value. It might have been overwritten with a string if we were sloppy with our code. So what does the function guarantee as its output? Normally we want to include that in the doc string, that multi-line bit of code of commenting I mentioned earlier with the 3 double quotes before and after the comment. We'd include something in there like, I assume the number of minutes is non-negative. I assume, or I mean for this function to not return anything other than a true or false value. That's some extra conditions that the programmer, i.e. you and me, can communicate to others for debugging purposes, for robustness checks, and for scientific consistency. So it helps to think about that, right? So when you're producing functions, the first task, in some sense, is taking the messy sort of understanding of what you want to do abstractly at a high level or in your own native language, and you start making it more precise, more mathematical in some sense. But you always have to remember, what assumptions are being made in the world, what has to be true before this function runs, and once somebody runs this function, what are they assuming to be true of the output of this function? It's very important because we don't want things to sort of break when they're being used. This is helpful for testing. So we talked a little bit about assertions earlier. So it's important from just a software engineering point of view. But because all of what we're talking about now is going to build towards deeper data science use cases and machine learning use cases, machine learning is a science, and because we're doing science, we have to ensure that what we're doing is reproducible and robust, so that if our experiments are run in our lab, so to speak, we want to make sure that whoever else is going to run our experiments in their lab with their data under maybe slightly different conditions will still get outputs that make sense and are more or less reproducible results of what we obtained. So that's not just good software engineering, that's good science, which again often goes hand in hand. So let's do a little bit of a setup. We're going to use a toy data set of study sessions again. The units here are going to be minutes of focused study. In this table here, each row is going to represent one study session. The day is a categorical variable, which we previously called a nominal scale. So these are just named things. Minutes is numeric. It's going to be, 0 means 0 minutes. This is what we call a ratio scale. Here's, as always, code that you can use and copy to reproduce yourself. This is going to be in a pandas object, a data frame. So here we have a bunch of columns, each of them with a label in text. And here at the bottom, I'm just writing out what this data frame looks like. Here it is in total. Here are indices in this first column. So data frames, and pandas already adds these indices for us. So we have Monday, we studied computer science for 25 minutes, and we studied math for 40 minutes, and so on. So let's dig into this a little bit deeper. So first we're going to focus, as well we should, on studying computer science. So here's our first question. Over this past week, how much time did we spend studying computer science, and what fraction of all of my computer science sessions would be described as long sessions? Again, a long session is 40 or more minutes. To answer these questions, we're going to use loops. We're going to use if conditional statements to basically answer this question or compute these quantities. We're going to wrap these rules inside of a function. So we can run a function to answer this question every week going forward. We have a nice stable function that we can use for different inputs of minutes, of weekly minutes. And then we're going to do some visualization, just a bit of a snapshot of what's to come. So we have a couple of things we're measuring here. Line 1 is total CS minutes. So I care, again, as I should, about how many total computer science minutes I'm going to be studying. So far, I haven't studied anything yet, so I'm going to store 0 there to begin with. In line 2, this is not counting the number of minutes, but the number of individual sessions that I've studied computer science. So far I haven't started or ended a single computer science session of studying yet, so I just initialize that with a 0. So that's the total number of CS sessions. Some of them will be long, some of them will be short. As I mentioned a moment ago, the question is going to be, one of the questions is going to be around the number of long CS sessions. So I have another variable that's going to just basically count that value as I look over my data frame. So that's also going to be 0 to begin with. As you can see, my variables here are named pretty well. I know I'm using the underscore here. I think there might even be some readability benefits to using the underscore here, because these underscores sort of separate different aspects of what I'm measuring. So in some cases, I'm measuring the total of something, actually only in one case. So I start off with total underscore something. In other cases, I'm counting a number of minutes. So in that case, it's the number of something. So num underscore something in variables on lines 2 and 3. In all of these cases, I'm studying CS, so I have CS here. This is just helpful to remind ourselves that we're talking about CS and not history and math. What is the thing that I'm totaling? Well, it's going to be minutes, which is part of my variable name. What is the number of things I'm counting? Well, on line 2, it's the number of sessions, and so on. Another aspect here is that you can kind of read these variable names almost as if they're, in this case, English. So I've removed prepositions like of here, but it's the total of CS minutes, or the number of CS sessions, or the number of long CS sessions. So the phrase that I would use to describe these quantities in English are converted more or less into variable names, in which each of these little sections demarcated by underscores is a word, and how I would define that phrase. So I have my study data, which I created just a moment ago, and the variable study data. So down here, as mentioned quickly, iter rows. Iter stands for iterate. This is a pandas function, which you can read about more at this link. This is going to let us loop over a data frame rows. Later we're going to prefer other ways of doing this, but since we're talking about for loops here, we're going to use iter rows. And conceptually, it might just make more sense at this point. This is just something we have to do because data frames is a somewhat more complicated object than just a list, which we saw previously in the example with minutes. Iter rows basically just transforms our data frame into a list object, which we can iterate over. And here we're going to be iterating over the rows that we saw a few moments ago. Just like we had before, we're doing a for loop. We have the built-in keyword for and the built-in keyword in. In most environments, you're going to see these being bold faces like they are here. And then everything, before, after for, and after in will be the variable names and then the thing we're iterating over. I just talked a little bit about the thing we're iterating over, defined by iter rows. What's happening over here? Now, if you click on this link over here, you're going to learn about what iter rows is returning. And unlike math functions, which we talked about a moment ago, code can return a couple of different values, which are kind of doing somewhat different things. And this is sort of breaking also not just what I mentioned before about the correspondence with math, because we're technically returning more than one value, but also it kind of seems to be breaking the idea that a function can do more than one task. In this case, the tasks are so closely related to one another that it's as if it's doing the same thing. I'll just mention briefly here that this first thing that's returned is the index of the row, and I don't care about the index right now, so I'm just kind of putting a placeholder in here. This underscore comma basically means like kind of throw away what's stored there. I don't care about the index returned by this iter rows function. What I really care about is the actual row of data in this in that row of the data frame. And for every iteration, i.e. in this case for every row of my data frame, store that row in the variable row. So now I can, given that I've put that row into this variable, I can now execute this block of code, which technically runs from lines 6 to 10. The first thing that I encounter is a conditional, an if statement. So here I have my keyword if, followed by the conditional. Here's the the operator that will compare a couple of two different things and return a true or false value. Here, I want to see whether or not the topic of the study session in this particular row is CS, because right now all I care about is CS, so I've written down, CS as the string, and I'm just comparing that string against whatever string is found in the topic field of that row. So like we saw earlier in another module, we have these square brackets, we have the name of the column in this case, which is topic. Row of the topic will resolve to CS or one of my other courses if this row is CS, i.e. if the value of this string is equal to CS, then I'm going to go ahead and run lines 7 through 10. So first of all, I've identified that this is computer science, so I'm going to add the total number of minutes studying computer science. I'm going to add to it, and what am I going to add to it? I'm going to add the value of minutes in this row. This plus equals is sort of a shorthand. Previously we saw the variable name that we're going to store a value in on the left, and then an equals, and then that same variable name plus some new quantity we're going to be adding. But why I keep on having to write this total underscore CS underscore minutes over and over again, plus equals just says take whatever value is stored in the variable mentioned on the left-hand side, add whatever is on the right-hand side, and then store that back in the variable mentioned on the left-hand side. So initially, the first time that this condition on line 6 is true, I'm going to run line 7. Total CS minutes was initially 0. So I'm going to add 0 to whatever is in that row under minutes, and I'm going to store that back in this variable total CS minutes. Also, I'm not just counting the total number of CS minutes studied, I'm also counting the number of computer science sessions at all. So because I'm referring to a new computer science session, I'm also going to run, at this point, the conditional, I'm also going to run this line 8, just add another study session to my counter num CS sessions, because this row represents one of my study sessions. I'm not totally done yet, so I'm trying to keep track of 3 separate variables: the total number of CS minutes studied, which I've obtained extra minutes accumulated from my minutes column in my row. I have just incremented the number of CS sessions because this is a new CS session, but I also want to check, is this a long session or not? A long session is defined as a session where the minutes is greater than or equal to 40. So I can again grab this number of minutes, which I made reference to a moment ago. I can compare it to 40. If it's greater than or equal to 40, then I'm going to increment the total number of long CS sessions. So if it's the case that it is, then num long CS sessions will take whatever value was stored previously, add 1 to it, and store that value back in the variable. And I'll keep on iterating through all of my rows in my data frame until I'm totally finished. I was interested in the fraction, so what proportion of all of my computer science sessions were long. So I have both of the variables I need for that fraction, right? So I have the total number of CS sessions that I have at all, which I've been accumulating on line 8. I also have the subset of those, which can be characterized as long, 40 minutes or more, which I've been accumulating in num long CS sessions. And I just have to divide one by the other to get the fraction of all of my CS sessions that can be characterized as long. Now I'm kind of done. Now I can print out the total number of CS minutes studied. Here, this is a somewhat different syntax than the one we saw previously. This one basically says take the value for my total CS minutes and write it out in this string. And so these curly brackets kind of indicate that I have to compute what is inside here. The long CS sessions is a fraction here. So this is basically computing the same thing I computed a moment ago. I invite you to check that this is actually correct. and then fractions long is what I computed a moment ago. This colon dot 2f basically just says this is going to be a floating point number. I want it evaluated to 2 decimal points of precision. So still looking through this example, what I've done here is I've reformatted the study data variable. I care about the elements in which the topic is computer science. I have grouped these by day. So whenever the days are the same, I group them together. I will be accumulating minutes. I'll be summing them together, and then I'm going to be doing a sort operation on them. This is a bit complicated. You don't need to be an expert or even to understand what's going on here. Suffice it to say that CS by day will be a new object that is just sort of a reformed version of just the minutes per day just in computer science, and then sorted. This last line here on line 8 just takes this new object I created and writes it to a frame and then prints it out here. So I have my CS minutes over all of my days. On Friday I studied 45 minutes, on Monday 25, and so on. Here's a little bit of code to draw a figure. This is going to draw a bar graph. It's going to give me my labels, my title, provide a tight layout, and then it's going to show the figure. And then this is basically just a visualization of the numbers that I had here. The numbers here are explicit, but sometimes it's just a bit helpful to look at things visually because, human cognition, we operate well on visual representations of things. So here is sort of a description of the number of computer science study that I've done for each day of the week over the course of all the data that I've accumulated in my original data frame object. So, same idea. If our goal is 2 long computer science sessions of study per week, we can compare these counts to that target. So here we can kind of iterate over each of these or find all the instances in which we have 40 or more in this table, or we can look at this bar graph, look at basically a line where we have the height is 40, and look for bars that is above that height. All right, so Friday, Sunday, and Wednesday, Friday, Sunday, and Wednesday are all above 40. One quick note here. Here we have the days of the week, Friday, Monday, Saturday, Sunday, Tuesday, Wednesday. That's the same order we see them down here. I'll just ask you to think a little bit about why you think that we got the days of the week in this order and not the more familiar one, Monday, Tuesday, Wednesday, and so on. Think about that a little bit and jot that down in whatever notebook you're keeping. So again, we're going to be aligning our metrics, the things that we're trying to compute, with the decisions we want to make in the real world. So in the real world, we might want to ask questions about whether or not the current approach to studying computer science is appropriate, or whether or not we should study some more computer science studying. So the metric we might include, or is the one we used a moment ago, is just the proportion of computer science sessions that are long. This is the total number of long CS sessions divided by the total number of CS sessions we've had. And we could use this to help make our decision. So this is percentage. So we can have a cost to, what decision we make based on this percentage, if we have a cutoff of percentage. If we have too few long sessions, that is to say we have, this proportion is too small, then that might mean that we are only studying computer science in a somewhat shallow way. Maybe we're switching between our various topics, computer science, math, history, too often, which creates some cognitive overhead, which limits the intake of knowledge in a study session, the effectiveness of a study session. So that's one way that having a percentage too small could provide some kind of cost. On the other hand, if you're trying to push this metric up and you're trying to make the total number of long CS sessions relative to the total number of CS sessions as high as possible, so you want many more long CS sessions, this can also be associated with some risks, some costs. You have a risk of burnout. It could also mean that because you're spending so much time studying computer science, this might mean you have less time for your other less interesting courses, or just less other courses generally. So you have a cost with having this, aiming to have this percentage too small. You have a cost with having this percentage be too large, and you have to kind of think about which costs you're more comfortable having and living with. There's something called this bounded optimality mindset, which comes up occasionally in different contexts. And this can be associated with the idea that we don't need a perfect plan. We just need a plan that's good enough given, real world budgets of time, of energy, of interest, whatever you value can help you make these decisions. You're never going to have a perfect trade-off between long CS sessions and total CS sessions, but you can think a little bit about the cost associated with high percentages and low percentages, evaluate these against your values, your personal values, and then remember that it doesn't have to be perfect. It just needs to be, this needs to start being good enough, and you operate from there. Here's a second example using the same sort of scenario. We want to answer the question about which topic is currently the most neglected and should get the next 60-minute block. So you've been accumulating all this data on your study sessions across days and across your different topics, and you want to be able to say, well, I'm neglecting history. Maybe I should have a next big block of studying. Studying should be for this neglected block. I'm not saying that's necessarily what you want to do in your real life, but you can imagine that this is the sort of goal that one of your classmates might have. So again, we're going to have a little function that's going to compute the total minutes for a given topic, and then use that to compute the totals for all of our topics, not just computer science now. And then we're going to visualize the totals and make a simple decision. So here's our code. I'm not going to walk through all of this because all of the concepts we have in this block of code is essentially the same we saw earlier. I welcome you to or invite you to copy this code, run it, maybe tweak it a little bit, and make sure you understand what every line of code here is doing. But it's fairly straightforward. Here we have a function called total minutes for topic, and it's going to return a total number of minutes spent on the given topic, and the topic is provided. Okay, so the result here is that we're going to have a total number of topics. This is just the unique values from the topic column in our pre-existing data frame study data. And then we're going to sort those unique values and store those in the variable topic. And then for every topic, I'll scroll over here. This is a bit of a side note. I didn't want to get down this path. Earlier I had 4 variable in list being sort of top level, like it is more or less here on line 6, at the beginning of a block of code that's going to be what we run for every iteration of the for loop. Python allows you to also put it, in other places, these for loops. And in this case, it's at the end of this big block, and it's basically saying at the end here, for every topic in this list of topics, which I just defined a moment ago, you're going to be doing this bit of code that precedes this for loop. This, regardless of how this became part of the Python standard, this also sort of matches how we would define a task in our language. So like do this for every X in list, right? So often we describe what we want to do first, and then we just specify afterwards that it's for every something in something. But anyway, so we have a list of topics. These are the unique values from our data frame. For every individual topic in that list of topics, do this. Run the total minutes for topic. And then we have our study data, which is our data frame. We have topic, which is the individual topic. We pass that to our function. We iterate. Because we're using curly brackets here, this is also a bit of a side note. Curly brackets essentially produce dictionaries or hash tables in Python. These are special data types, which are kind of like lists in some way, except every element in this structure has a key, which has a name, a string, and then it has a value that key in some sense points to. So here the key, which is the first part, and then there's a colon, and then there's the value. The key we just get from the topic. So one topic is CS, for example. This is one of the keys in this dictionary. What is the value of topic? Well, I get that value from running this function, topic, total minutes for topic, with these arguments. This executes this function from lines 1 to 9. I obtain some total from this return line on line 9. And that value is stored as the value for key, in this case CS, in this dictionary. Okay, hope that makes sense. So here we encapsulate this pattern loop and add minutes for a topic in one place. If we later want to change this rule, so if we later wanted to only ignore sessions where we only study for 10 minutes or less, we can easily add that in a small place over here in this function. So as we're iterating over all of the rows for this particular topic and adding all the minutes studied, maybe I don't want to add a number of minutes for a session that only had 5 minutes of study, that it wasn't enough studying to really count, so I'd add some conditional, but between what is now lines 7 and 8, that just checks to see whether row of minutes is greater than 10, and only if so would I add to my running total count. In fact, I strongly recommend that you go ahead and try editing that function to perform that check. Here again, I'm just converting these topic totals from our series, converting this to another frame and then printing it out in a nice form that is easy to understand. So we have all of our topics here in rows. We have the total minutes we've been accumulating as columns. There's only one column. And then we visualize what I previously showed as output a moment ago. And then again, I want to create a bar graph with labels and titles and title layout. I want to show it. So this basically is a visualization of the table. Now I can kind of visually see not just numeric value of the total number of minutes, but I can kind of visually see the extent to which computer science has dominated our studying. And here I have a little bit of code here. This is also a little bit, this IDX min just gets the index with the minimum value in this topic totals series, which I computed a moment ago, stores its value in least topic and prints it out. You can obviously see this yourself. The point is, I've decided that, well, history has the smallest value of total studying minutes by all these topics. So, the decision could be to balance things out. The least studied topic, in this case history, should get the next 60-minute block. So afterwards, this bar graph would be 60 minutes taller after that new session, at least in theory. So we haven't really done any fancy machine learning yet, although we are building piece by piece towards that. But we want to be able to evaluate our code, even the simple code we've produced in this module, using a few simple metrics. The first one is readability. So can a teammate understand this function very quickly, ideally under 30 seconds? The 30 seconds threshold is also kind of arbitrary, but this function should be readable. Sometimes people suggest that a function should be able to fit on one screen at a time. You should be able to see the whole thing at once. That, of course, assumes something about the layout of your screen and the window and so on, so not everyone uses it, but generally it should be nice and tight. Does the code avoid repeated logic? This is the first kind of problem we encountered in this module. Don't repeat yourself. Don't run multiple conditions on the same kind of thing. Try to compress as much as possible, to the extent possible. So don't repeat yourself, which is the first lesson we learned. How testable is this? We didn't write any assertions in this module, but we talked about assertions in a previous module, and you can kind of check, is the total number of minutes greater than or equal to 0 would be an assertion we might want to add. And again, this is left as an exercise to you. Is it robust? So what would happen if the data set we're providing as an input to our function is empty, or a topic is missing, or some other problem might exist? You should go ahead and try to break these functions, come up with clever ways that a function would would either return a wrong value or just break with an error, and provide that and evaluate it. So all of this, readability, duplication, testability, and robustness, is in some sense rudimentary software engineering, but it touches on the core themes of reproducibility, robustness, evidence, precise communication, and that all has to do with the underlying current of this is part of science, this is data science. Science, a big part of science is communication, that has to be done precisely. So even when we're writing functions, we have comments. In some sense, the function itself is a communication to the reader as to what the code is doing. So we have to be as precise as possible. As always, we want to be able to touch on some ethical considerations. Even the simplest scripts or functions can have ethical considerations. So we talked about branching, so like conditionals. You might be inspired, or you might be you might be incentivized to check whether or not a certain country has a certain value. Like, is the data from a particular country? In many cases, it might make a lot of sense. Like maybe you certainly only care about data from Canada and you want to exclude data from other countries. But it's possible that if you're performing these kinds of conditions without some careful thought, occasionally a high-level abstract notion can infect some of your coding, and checking for values of variables in this way can sometimes have unintended consequences. You might silently drop some data. So if the minutes studied is less than or equal to 0, then you might continue without running some additional code. If you don't log this, or if you don't include some other output to whoever's running this code, this might hide something that should have been logged. Like, if somebody is including negative minutes in their data and you're just skipping over it and ignoring it and moving on, then this misses the opportunity to communicate to whoever provided the data that something might be wrong. Like, why could they possibly have negative minutes? Maybe they've communicated to you that negative minutes has some particular meaning, and it's not just an accident, but all of those things are assumed, and we always have to check our assumptions. So it's usually better if you're running any logic, like we have here on the silently drop data line. It's better to log it and then double check afterwards on why these conditions were met. So we want to keep decision rules basically small, well-named functions, easy to review. We want to add tests and comments. We added some comments earlier on some branches. Whenever there's a branch that might treat people differently, that might separate out people from different national origins differently, we need to test whether or not those conditions have very different outcomes, and we're going to need to comment why we're doing this. We shouldn't just say well, if someone comes from this particular country, perform this code, everyone else perform that code. There should be a communicated reason for that bifurcation or that separation. We want to be able to also explicitly express what we assumed about the data generating process. So the person studying these minutes, if something is not captured in the data set, which we assumed to be known, that is still something that we want to communicate, to be explicit about. So, as is the case on many of these modules, we're going to do a quick check. So you are going to go through these questions and come to class with your solutions for them. I want you can run this yourself, of course, but I want you to look at this code and think about what does this code print. If you don't understand any particular bit of code here, like you forget what this percentage sign might mean, you're perfectly welcome to go online to search or ask questions about any aspect of this code. How many times is the string hello printed? And what is the final value of count printed here at the bottom? So on paper, or in your mind, walk through this code and try to figure out what the answers to this question are, and before you run it. Here is a kind of a multiple choice question. Why is it usually better to wrap repeated logic in a function instead of copying and pasting the same code one after the other? So think about this a little bit. As always, if you think that there's some other option, some option E, which is better than A, B, C, or D, or maybe some combination of these options, feel free to bring that to class and with your explanation. And I want you to write a small function that converts Celsius to Fahrenheit. So we didn't talk anything about Celsius or Fahrenheit today, so you'll have to go online to figure out what the relationship is, but you should be able to write this kind of function in Python yourself already. So we talked a little bit about for loops and conditionals. In the next module, we'll run doc tests and debugging basics. So this will turn the expectations and our assumptions into things we can actually test. Fairly soon, we'll get deeper into pandas for larger tabular data sets, and loops will be transformed into more powerful one-liners. I would like you to keep practicing small pieces of code, write tiny, well-named functions, and think about pre- and post-conditions. We'll be returning to this over and over again throughout the course, so it's a good idea to have practice. And the more practice you do, the more you prepare for future modules, the more you and your teammates or teammate will thank you. Thanks so much.